Alkenes. Alkenes, unsaturated aliphatic hydrocarbons containing two hydrogen atoms less than the corresponding alkanes and which are characterized by the presence of a double bond in their molecules are called alkenes. These are also called olefins. Latin olefiant is equal to oil forming. Since the lower members of this class like ethylene forms oily products on reaction with halogens such as chlorine and bromine, their general formula is CnH2n where N is equal to 2, 3, 4, etc. Unsaturated hydrocarbons containing 2 and 3 double bonds are also known. These are called alkadienes and alkadrienes respectively. The general formula of alkadienes is CnH2n minus 2 where N is equal to 4, 5, 6, etc. Unsaturated The term polyene is used for unsaturated hydrocarbons containing several, usually more than 4 double bonds. Nomenclature of alkenes. Alkenes are named both by their common and IUPAC names. Common system. In the common system, unsaturated hydrocarbons containing a double bond are called olefins. The name of an individual olefin is obtained by replacing the suffix "ane" from the name of the corresponding alkane by "ylene". Common name is equal to alkane minus ane plus ylene is equal to alkylene. In case of isomeric olefins, the position of the double bond is indicated by Greek letters alpha, beta, gamma, delta, etc. The numbering being done from a direction which gives the lowest Greek alphabet to the carbon atom carrying the double bond. Sometimes prefixes such as iso are also used for the branched chain isomers. IUPAC system. In the IUPAC system, the unsaturated hydrocarbons containing a double bond are called alkenes. The name of the individual alkene is derived by replacing the suffix "ane" of the corresponding alkane by "ene". Following rules are generally followed while naming alkenes according to IUPAC system. The longest carbon chain containing the double bond is chosen as the parent alkene. The position of the double bond and the substituents, if any, are indicated by Arabic numerals, namely 1, 2, 3, etc. Numbering being done from that side which gives the lowest number to the double bond. If while numbering the chain, the double bond receives the same number from either side, the corresponding chain is numbered in such a way that the substituent gets the lowest number. The position of the substituent separated by hyphen is either prefixed to the name of the alkene or is placed before the suffix "ene". Alkenyl groups. The monovalent alkenyl group obtained by removing a hydrogen atom from ethylene is called vinyl group or ethinyl group, and that derived from propylene by removing a hydrogen atom from the doubly bonded carbon atoms is called propenyl group. If, however, a hydrogen atom is removed from the methyl group of propylene, the alkenyl group is called allyl group. Methods of formation of alkenes. Alkenes can be prepared in the laboratory by the following general methods. First is dehydrohalogenation of alkyl halides, removal of the elements of hydrogen halides like HCl, HBr or HI from the adjacent carbon atoms of alkyl halide is called dehydrohalogenation. Dehydrohalogenation of alkyl halides gives fair to good yields of alkenes and is generally carried out by heating an alkyl halide with a strong base such as sodium ethoxide or a concentrated alcoholic solution of potassium hydroxide. For example, ethyl bromide plus alcoholic KOH gives ethylene plus KBr plus H2O. Then 1-chloropropane gives alcoholic KOH on heating gives propene plus KCl plus H2O. Mechanism. Dehydrohalogenation of alkyl halide is an example of elimination reactions. Elimination reactions occur by a number of different mechanisms, but we shall discuss here only two of them, that is E2 and E1. The dehydrohalogenation of a majority of primary alkyl halides occurs by E2 mechanism. Kinetic studies of this reaction reveal that the reaction follows second-order kinetics. The rate of the reaction is proportional to the concentration of both the alkyl halide and the base. Rate proportional to alkyl halide and the base. This means that E2 reaction is a one-step process and occurs through a transition state. As the hydroxide ion begins to abstract the proton from the beta carbon atom,
Next to the carbon atom carrying the halogen atom, the carbon-hydrogen sigma bond begins to break, a new carbon-carbon pi bond begins to form, and the leaving group, that is the halogen atom from the alpha carbon, begins to depart, taking with it the electron pair forming the carbon-halogen sigma bond as shown below. Thus, dehydrohalogenation of alkyl halides occurs by a concerted mechanism in which the carbon-hydrogen and carbon-halogen sigma bonds are broken and carbon-carbon pi bond is formed approximately at the same time. An important aspect of elimination reactions is that they are always accompanied by substitution reactions as well. Thus, in the above reactions, along with ethylene, some ethyl alcohol is also formed. Stereochemistry. It has been observed that E2 elimination reactions are much more facile when more departing groups, that is hydrogen and chlorine, are trans with respect to each other than cis. For example, trans 2-bromo-2-butene forms dimethyl acetylene more readily than the cis isomer. Even elimination unimolecular reaction. Many secondary and tertiary alkyl halides undergo elimination reactions when heated in an ionizing solvent. For example, tertiary butyl bromide, when heated in alcohol, undergoes dehydrobromination to form isobutylene. Studies on this reaction have indicated that it follows first order kinetics, that is, the rate of a reaction is proportional to the concentration of alkyl halide only. Rate proportional to the concentration of alkyl halide. This law suggests that only alkyl halide is taking part in the rate determining step of the reaction. This means that even reactions of two-step process involving the intermediate formation of carbocations. The first step involves the ionization of the alkyl halide to form a carbocation. This step is slow and hence is the rate determining step of the reaction. Second step involves the rapid loss of a proton to form the alkene. This step is fast and hence does not affect the rate of a reaction. It may be noted here that the case of even reaction depends upon the stability of the carbocation. Further, unlike E2 reactions, even reactions have no stereochemical preferences since they involve carbocations which are planar chemical species. However, like E2 reactions, even reactions are also accompanied by substitution SN1 reactions. Regiochemistry or orientation of E2 and even reactions. Sadzev rule. An interesting feature of elimination reactions is that a mixture of isomeric alkenes is invariably formed if the structure of the alkyl halide is such that the double bond can be formed in two possible directions. Out of these two isomeric alkenes, the alkene which is more stable is formed in the greater amount, but we know that greater the number of substituents across the doubly bonded carbon atoms, more stable is the alkene. Thus, in almost all the even and most of the E2 reactions, the more highly substituted alkene predominates. This generalization is called Sadzev rule. For example, dehydrobromination of 2-bromobutane gives the more stable 2-butene in 80% yield and the less stable 1-butene in 20% yield. 2-bromobutane when treated with alcoholic QH gives 1-butene in 20% yield and 2-butene in 80% yield. Further, the more highly substituted alkene can often exist as cis and trans isomers due to the greater stability of the trans over the corresponding cis isomers. Trans alkenes are the predominant products of even and E2 reactions. Regiochemistry or orientation of E2 and even reactions. ZZF rule. An interesting feature of elimination reactions is that a mixture of isomeric alkenes is invariably formed if the structure of the alkyl halides is such that the doubly bonded can be formed in two possible directions. Out of these two isomeric alkenes, the alkene which is more stable is formed in greater amount, but we know that greater the number of substituents across the double bond, more stable is the alkene. Thus, in almost all the even and most of the A2 reactions, the more highly substituted alkene predominates. This generalization is called Sedsev rule. Further, dehydrobromination of 2-bromobutane gives the more stable 2-butene in 80% yield and the less stable 1-butene in 20% yield. Dehalogenation of vicinal dihalides. The dihalogen compounds in which the two halogen atoms are attached to the adjacent carbon atom are called vicinal dihalides. These, when heated with zinc dust, lose a molecule of halogen as zinc halide to form alkenes. The reaction is known as dehalogenation. Thus, ethylene bromide, when react with zinc in the presence of alcohol, gives ethene and zinc bromide as the product. Propylene bromide, when react with alcohol, gives propene and zinc bromide as the product. The reaction is not a useful method for the preparation of alkenes since the dihalides needed for the purpose are themselves prepared from alkenes by the addition of halogens. However, this method is very suitable for purification of compounds containing double bonds and for the protection of carbon-carbon double bond in chemical reactions. Dehalogenation of vicinal dihalides occur by an E2 mechanism. 1,2-dibromopropene by the transition state gives propene as the product. By dehydration we means removal of a molecule of water. Alcohols on dehydration gives alkenes. The dehydration is carried out by heating a suitable alcohol with protonic acid such as concentrated sulfuric acid or concentrated phosphoric acid. Lewis acid such as anhydrous zinc chloride or alumina can also be used. Alcohol on treatment with sulfuric acid gives alkene as the product and water as the byproduct. Actual temperature and the strength of the acid, however, depends upon the nature of alcohol used. For example, primary alcohols such as ethyl alcohol and propyl alcohol undergo dehydration when heated, such as 95% H2SO4 at 443 Kelvin to 453 Kelvin to give ethylene and propylene respectively. Ethyl alcohol in 95% hydrogen sulfuric acid gives ethylene as the product, and propyl alcohol in 95% sulfuric acid gives propylene as the product. On the other hand, dehydration of secondary and tertiary alcohols occur with dilute H2SO4 and at lower temperatures. For example, isopropyl alcohol secondary alcohol 60% H2SO4 yield में propylene देगा. टर्शियरी ब्यूटाइल अल्कोहल इन 20% सल्फ्यूरिक एसिड के अंदर आइसोब्यूटिलीन देगा. Because isobutylene is formed because it is formed by the elimination of tertiary alcohol, while propylene is formed because it is formed by carbocation mechanisms and not by the elimination, although elimination is preferred in last when hydrogen removes and this propylene is formed, but that occurs by a secondary carbocation mechanism, while this occurs while the formation of